In this lecture, I want to talk about abstract data types and their realization as data structures. An abstract data type really is nothing but an abstract set of operations with some meaning associated to them. So as an example, think about a stack of plates. If we wanted to work with a stack of plates, we can add things to the top. We can take them off the top. We have a hard time taking them from the bottom. In a computer, we can represent an analogy of this as what's called a stack. And the operations we expect to have on such a stack are the ability to create new stacks, the ability to add items to a stack, and the ability to remove an item that has been added, assuming there is one. And then, because we need to assume that there is something there, we need to be able to tell whether or not a stack is empty. These ideas are realized in Java as follows. We have a class used to represent the abstract type, and we have methods and constructors to represent the operations. There's a special type of function in Java called a constructor, which is used to build new objects. When we invoke this special type of function, we use a special syntax. We use the new operation in order to invoke this. And this will create a new object for us, which we can store. We then have methods that we can invoke on the object. In this case, we'd write them as isEmpty, push, and pop. They have associated types. IsEmpty takes nothing and returns a Boolean. Push takes a string and gives nothing. Pop takes nothing and gives a string. So we can invoke these, for example, to push on the stack. We push a string, and the stack is indicated on the left-hand side of a dot. This is common in object-oriented languages. There's this idea that I'm working with some object, and the push method is being invoked on that object. Similarly, I can pop from a stack if I have one, and what I'll get back is a string. Now it's important I don't invoke the pop operation if the stack is empty, and therefore this is typically guarded by a call to isEmpty. So this is an abstract type. Note that I haven't told you how any of these operations are implemented. I've just said what the operations are and how they should behave. When we look at a specific implementation of such a type, this is what we call a data structure. And the most important choice we make in a data structure is how to store the data in memory. In this case, we have all the items that we're pushing into our stack. We have to decide how to organize those in memory. For the stack, we're going to look at two choices. One is to put all of the items contiguously in an array, and the other is to spread them around the memory and to connect them via links. The choice of the storage pattern affects the performance of all the operations. To start off with, we'll be working with a very simple example, which is a fixed capacity stack where everything is stored contiguously in memory. Now we're going to look at this code, and it's already quite a lot to digest, so let's take it in pieces. We'll start by looking at the main method and how it executes. So I've run this and generated pictures from the execution. And you can see here, I'm first invoking my trace.run method here on line 33, and that's where the pictures will start. And if I move forward here on line 34, I'm waiting to form a stack. So what's happening here on line 34 is I will create a fixed capacity stack of strings, and it's going to have capacity 7. So let's see what that looks like. I've got a fixed capacity stack of strings with capacity 7. This is represented as an array with 7 slots. There's also a variable in associated with this stack that tells me how many of those slots are currently occupied. On the next line, I'm going to create a second stack, and this one will have a different capacity. So this stack has capacity 3. Note that it's also got none of those slots occupied. In the program, I've used different variable names for the stack. So stack 1 is the name of the first stack. Stack 2 is the name of the second. Note that I also have the args array. This is simply because my main program always has an args array, and it's initialized in this case to an empty array. On line 36, what are we going to do? We're going to invoke push on this first stack. When I do that, note that 2 changes happen. First, in goes from 0 to 1. And second, 1 slot gets occupied. I'm then going to go to the second stack and push. And again, we'll note that in changes as well as a slot gets occupied. I'm going to continue like this for a little bit, alternating between stack 1 and stack 2. Between stack 1 and stack 2, until we get to line 43. At this point, I'm going to pop from the 2 stacks. So we'll pop out of stack 2 first, and we'll get out FDB. Then we'll pop out of stack 1, and we'll get GECA. So note the items will come out in the reverse order that we put them in. So the first thing that we're going to get out is F. Note that this slot is now free, so the capacity has increased and the number of occupied slots has decreased. So we're now going to pop again from stack number 2 at line 44, and we'll now have only 1 slot occupied. Then finally, we'll do it again, and now we have no slots occupied, and therefore the stack will be empty and the loop exits. So at this point, we'll now pop everything off the first stack, and it proceeds sort of as you would expect. We go down 3, 2, 1, again, taking the things in reverse order. So that's how we use the stack, and you can sort of see how they're implemented. Let me just show you some things that I've done here. I've done a few things to simplify the view. If you actually look at the full details of these objects, you would actually see more. So in Eclipse's debugger view, you would actually not see quite exactly what I showed you. So let me show the built-in objects here, and you can sort of see what those actually look like in Java. And in particular, what I've simplified here is the view of strings. Strings are themselves objects. So when I push a string, I'm actually pushing a string that has a couple of fields itself. So these can get quite complex. And you can see the values here just being shown as numbers. Those are the characters stored in the array. So the first thing I pushed was A, and that's represented as ASCII 97. The second thing I pushed was B, which is ASCII 98. So this kind of stuff is important sometimes to understand, but at other times it's just confusing. So for the most part, I prefer to work with this elided. I believe that it's much easier to read when we just give the more abstract representation of the strings. The other thing I'm doing in these diagrams is showing arrows for object references. And this is meant to be very intuitive and very helpful, but sometimes it's useful to just sort of think about what's going on under the hood. So let's look at I put in the ability to show object IDs redundantly. So what this will do is it will show you all of the local variables explicitly as a sort of array of local variables in each object. So already you can see the difference here. The main method has a argument, which is a string array. In Java, these objects all have object identifiers. These correspond, or you can think of them as unique identifiers for the object. In an implementation, they actually correspond to addresses in memory. But this object has identifier number 140. And what our main method actually has is a local variable for those arguments. So as we get more local variables, we get more and more of these represented here in the main method. And you can see here each stack has an array, and that's actually sort of a local variable of the stack. So it's stored with the stack, and that's pointing to this object here. For the most part, I don't think that having these redundant IDs is helpful. I think the arrow notation is much more intuitive for us people. So, but in the machine, what's stored are not little arrows. There's no arrows in the computer. It's storing just numbers, but those numbers help connect one object to another. So what's stored in this main is just 3 numbers. Those numbers correspond to the addresses of these 3 objects, which are here represented by those object identity. So I will turn these things off because for the most part they just create a lot of clutter, and the original diagrams are fairly intuitive. You get all the information you can see or need to see here, but the important thing to note here is that when you see these 3 arrows coming out, the solid arrows, those indicate that this method has 3 local variables and they're pointing to those objects. Now let's look a little bit in more detail at the implementation of these methods. So let's look at the implementation of the constructor, push, and pop. We can see all of these methods as they execute. I'll do this by simply drawing all of the steps of the program, and then we can watch the complete program executing in all of its glorious detail. On line 34, we invoke the constructor with argument 7. That causes Java to do a few things. The first thing is Java will allocate space for an object and set all of the fields of that object to 0. What are fields? They are variable names that are used outside of any method in a class declaration. So here on lines 4 and 5, I have 2 variables declared. One is a, one is in. These are not variables in any method. They are instead variables that are just floating in the class. And these are called fields. The fields of the class are allocated when an object of that class is allocated. And they're all initialized to 0. 0 is used in Java at all types, and it has a different interpretation depending upon the type. So you can see that at numeric types, 0 is just 0. At object types, 0 is null. And A here is a reference to an object that's a string array. So therefore it's given the value null. If I had a Boolean field, it would be false initially. Now, what happens is after this object is allocated, it's associated with a special name in Java, this. This is a name I can use in constructors and in methods, and it refers to the object upon which the constructor or method is invoked. In this case, Java allocates space for this object, and then it executes the constructor code relative to that object. So what we're doing on line 9 is to allocate a string array, there it is, and to associate that string array with field A. Note that field A is no longer null. It is now an object reference. And so in the visualizer, that's shown not as null, but as a pointer to an array. On line 10, we initialize in to 0. This actually doesn't do anything because in is already 0. So once the constructor is finished, it will return, and you can see here on line 34, we're going to return this fixed capacity stack of strings back to the main method. So on line 34, what happens when I get back is that I will associate that new object with the variable stack1. So note that stack1 is a local variable of the main method, and therefore it's shown in red here. So objects are purple, methods are red, or method calls are red, and arrays are blue. What we'll do now is repeat this entire process on another object with capacity 3. When it gets back to the main method, it will actually be called stack2. At this point, we're going to invoke on line 36 the push method on stack1. Let's just go to the push method in the debugger and see what it does. So here's the invocation of the push method from main. And it's worth noting that the push method, in addition to having the ability to return back to main, it also has a this pointer. Which stack is it pointing to? Well, it's pointing to the stack that was on the left-hand side of the push operation. So it's pointing to stack 1 from our main program, the stack with 7 slots. In addition, when we invoke push, we passed a parameter. So we passed a pointer to the string a. And note that that is here as a parameter to the method. What is push going to do? Well, at line 15, it checks to see if the item is null. If so, it throws an exception. This is not null, it's a string. Therefore, we will move happily to the next line. On line 16, we check if we've overflowed the array. If so, we'll throw an exception. You've tried to add too many things. Then the real action happens on line 17, where we will take the item parameter and store that in a of n. So note that n is 0, so we'll store the parameter in a of n. And note, for a brief moment, things look kind of bad in my array. There's something there, but it is not yet indicated that I have stored something there. So it's important on line 18 that I increment in to indicate that that's there. So we expect the invariant of this structure is that the number of things should correspond to the number of non-null slots in this array. So once we've finished those two operations, we can now return back. Note that this method doesn't return anything. There's no return value. So we'll just immediately go back to line 37. We'll then push a bunch of stuff. So we're going to push back and forth for a while until we get sufficient values in both arrays. So the last thing I'm pushing is G, which is being pushed in stack 1. You might note as I go through these pictures that the layout is not stable. Sometimes stack 2 will go on the left, sometimes stack 1 is on the left. And this is because of the algorithm used by GraphViz. It's you do need to read the names to make sure you understand what's going on. GraphViz has its own ideas of how pictures should be drawn, and each of these pictures is drawn individually. In any case, after we've pushed in the last item, we then invoke the isEmpty method. That's first invoked on stack 2. So on stack 2, we will invoke the isEmpty method. So on line 13, what do? We just return whether or not n is equal to 0. In this case, n is not equal to 0. It's equal to 3, so that'll return false. So therefore, we will go to line 44, and that will invoke pop. So the pop method is now going to pop off of stack 2. And what does the code for pop do? Well, it looks to see if the stack is empty. And in this case, that's not true. So what we'll do is decrement in. There we decrement in on line 22. Then on line 23, we will store the string that I want to return. So in this case, it's going to be a of n. So that is a of 2. So note that in was 3. So 3 is beyond the end of this. So if I tried to push at this point, I would get an exception. But I'm good. I'm trying to pop, not push. So what I'll do is decrement into 2. And now I can look at the second element of the array. It's 0, 1, 2, 0 indexed, right? So at index 2, we have the letter F. So what we'll do is store that as the result. So note that's a local variable of the pop method. So it now has an extra local variable result. And what I'm going to do is, so that the element is no longer stored in the array, is to write null there, which on the picture makes it simply disappear. So you can see blank elements of an array are represented as null. And that's how pop works. It then returns the result back to the main program. So that's returned to the main program, which can then print it out. And now we'll simply do this over and over again, calling isEmpty and pop over and over again to pop out all the elements from the 2 arrays. And once we're done, well, we're done. So that's the execution of this version of the code. The important thing I want you to notice here is how local variables are stored in the invocations of methods, and fields are stored with objects.